But the important part is that the theorem says that the ground state energy can always be written in terms of only one electron density. And I will prove that theorem. But after that you will realize how. Because I am not able to do even for Hartree form, as I showed you. So how is it written? That's a mystery that continues till today. How do I get the proper density function? Yes?
Yeah, so one question not related to what...
So now to understand the Wenberg-Kohn theorem. Wenberg and Kohn had two theorems actually. And it's a very important theorem. The first one is called Wenberg-Kohn theorem 1. So HK1. Again, this was proposed in 1964, very celebrated theorem, which says that, and actually the theorem actually is a little bit loaded than what we say. It says that there is a unique correspondence between the external potential and the electron density. It only says external potential, actually. So why external potential is very important. In fact, this is something that you should understand. If you look at the Hamiltonian of any n particle, let's say any n particle Hamiltonian, how are they distinguished? Every n particle Hamiltonian has, or let's say electron, has the same form, minus half Laplacian, plus 1 by Rij. Where does it differ? It differs in the potential. It's a way of looking at it. So the potential, which may be the one particle potential, V of R, right? This is the only part which distinguishes from one n particle Hamiltonian to another n particle Hamiltonian. It's a very interesting thought. Whether it's an atom or a molecule, if they're isoelectronic, the Hamiltonian is same except this. So if you look at ammonia, which is a 10 electron problem, and water, which is also a 10 electron, Hamiltonian is same except for the potential. What is the potential? That the 10 electrons of ammonia are attracted by nitrogen and 3 hydrogens. Whereas for water, they are attracted by 1 oxygen and 2 hydrogens. So that potential is the only thing that defines. So a system is only differs in external potential. So the Wenberg and Kohn said that there is a unique correspondence between this external potential and the electron density of the system. So this is where it came, because if for a ground state, of course for the ground state. So for the ground state, if I know the rho of R, it uniquely tells me the potential, V of R, one particle potential. And then of course it means I can find out the energy, because the moment I know V of R, I know H. If I know H, I know energy. So remember, how do I know energy? That he is not telling me. But it says that if I know the electron density, I know the energy. It's the existence theory. Uniquely, that is very important. Because for a given rho of R, there is a unique potential. That unique is a very important word. Which means, given two different potentials, there has to be a different densities. And this is what he actually proves, very interestingly, that it takes different potentials and shows that they must correspond to two different densities.
So what kind of potential are these? Like previously you are getting the mean field kind of potential.
Yeah, this is also, no, this is actual Hamiltonian.
This is actual.
No, the main field comes from here. This is actual potential in Hamiltonian.
So this is external potential.
External potential. So V external. Right. So this is like nuclear attraction. Could be electric field, whatever. But this is an external potential. So he looked at the electronic system in the following manner. Forget about nucleus. You have only n electrons and then an external potential. That external potential is of course very important. That is what is making an atom, molecule, because they are the nuclei. So he says the electronic part is just identical. Kinetic and electron-electron repulsor plus external potential. Which I can write simply capital V. Doesn't matter how I write. I'm just writing a sum over V of Ri, because for our external potential it's a one body potential, but I can write capital V.
So that's crucial. So one body.
This is one body. No, but in the theorem, no.
Theorem.
Theorem is just external. I'm actually writing because that's what the students will understand. And we'll be discussing all external potential, one body potential. But yeah, theorem is general. So what it means is that if I have two different potentials, they can't correspond to the same density. So that is essentially what Wenberg and Kohn proved actually, that it is formally not possible. And the proof is very elegant because it actually takes recourse to a simple variation method. A very simple variation method. So it starts from two Hamiltonians. So let's say I have H, which is kinetic energy, let's say P or whatever, plus V electron, plus the external V. So this is important. And then I have another V external, which is V external prime. Rest will all be same, that defines your H prime. Okay? If densities are same, it means the wave function is same. So it says that if I now want to have a same wave function for both H and H prime, that is not possible because of a very simple variation method. And he applies the variation method there very, very nicely. So for example, if I have H, of course this will have a psi in general, this will have a psi prime. If I do a solution, I will have a psi and a psi prime. So then I can calculate energy for this, E naught. Again, it's a ground state energy. For this, I'm going to calculate E naught prime. Okay, each of them will be with an upper bound. Of course, they have an upper bound principle and so on. So let's assume that I calculate a variation method in which for Hamiltonian I use psi prime, and for Hamiltonian prime I use psi. So let me just write this now. So if I write an expectation value of psi H prime psi, this will definitely be greater than or equal to E naught prime. You agree? Because what is E naught prime? It is psi naught prime, psi prime, H prime psi. Right. But now for H prime Hamiltonian, I have taken psi, the eigenfunction of the Hamiltonian, H, not H prime. Hence, of course, it is not going to be equal to E naught prime, but it must be greater than or equal to E naught prime. Because my variation theorem says that any arbitrary function, if I calculate the average value, it is always greater than or equal to its exact energy. Now remember, this psi is not an eigenfunction of H prime. It's an eigenfunction of H, hence it's a different function as far as H prime is concerned. This must only be greater than or equal to E naught. Is it clear? So I can write an expression that psi, now I write what is H prime in terms of H. If I write in terms of H, then you can see that H prime is nothing but H plus V prime minus V. Remember, these external potentials are different, V and V prime. So I can write H prime as this psi greater than or equal to E naught prime. Okay? Note now, psi H psi is nothing but E0. So E0 plus, and then I can write, if this is one particle, it's easy to show that psi V prime minus V psi is nothing but integral rho of R, V of R, V of prime of R, or V R prime minus V of R, V R. That's very easy to show because V prime minus V is also one particle. And one particle part is very easy to write in terms of density. I told you already that just write the density multiplied with this. So I have got this E naught plus this, and this is of course greater than or equal to E naught prime. In particular, if psi and psi prime is actually different, then this equal to has no meaning. It has to be actually greater, because they are different, but I am writing still equal. Now do the reverse. So take the Hamiltonian and take psi prime. Just take the inverse. So this is now going to be greater than or equal to E naught. And do the same expansion. I can easily see that you write E naught prime plus integral rho of r, v of r minus v of r prime. Or v prime of r, sorry. V of r. It will be exactly opposite. And this will be greater than or equal to E naught. Right? Now the contention was this. In case V is different from V prime, the equality is always going to be inequality. It will have to be different. So this was a thing that a lot of people discussed. Is it really true? So which means I have to remove this. If literally V is different from V prime, they have to be greater because they are different. Right? It cannot really be equal. When is it going to equal? When V is equal to V prime. Or psi is equal to psi prime. Because equality is given only because I am varying over entire space. But if I know definitely psi is different from psi prime, this must be greater than E naught prime. And the other one must be greater than E naught. Then what Weinberg and Cohn did was just to add these two equations. If you add these two equations, you see what you get. You get E naught plus E naught prime. And now it is very easy to show that this is negative of this. Remember, they have the same density. So what did I assume? I assumed two different Hamiltonians, which will give me two different densities. So I only assumed that although I have two psi and psi primes, their densities are same. Then Weinberg and Cohn shows that this is impossible because you have E naught plus E naught prime. This cancels. How can this be greater than E naught plus E naught prime? Right? So you reach an absurdity. So that's an absurdity. So which means this assumption of these two densities were wrong. That these two densities being common are wrong. Hence, it says that if I have two different external potentials, two different psis, so this is psi, this is psi prime. Two different psis, my density also has to be two different. So this was the very key part. That if I know the density, then the argument, actually the argument is more complicated. This is all that Weinberg and Cohn proved. That is the reason it was so difficult. Does it say ground state energy is unit functional of density? No, it does not automatically say this. He only said, if I have two different potentials, it must have two different densities. That's all he said. But now he argues back that given a density, I know exactly what is V external. There is a unique correspondence. How do you know V external? That he never told. That's a key problem. So given a rho, my V external is unique. It cannot be V prime. Or it cannot be another V external. If V external is unique, H is unique. Right? If H is unique, E naught is unique. It's a very interesting way of arguing. He said, if I know the density, I know uniquely the ground state energy. But the proof is just this. So you may have your own interpretation and think about it. Did he make a mistake? A lot of people said, no, the proof is correct, but Weinberg and Cohn's further interpretation is wrong. But there has been a lot of debate. And almost everybody said, no, there is no argument. What Weinberg and Cohn said that if I know a particular density, I know it corresponds to a particular Hamiltonian. And hence it corresponds to a particular energy. That's all he said. Does it mean energy can be written as a unique function of density? I don't know. It's your interpretation. He only said if I know the ground state density. Why it is ground state? Because variation theorem is applicable only to ground state. Or states, lowest state of the same symmetry. I don't want to complicate that variation method. There is orthogonality states are also there. But let's say ground state for the time being. So if I know the ground state density, I know it corresponds to a specific psi, specific V external because of this theorem. V external cannot be same. Specific V external defines H defines E naught. So which means a density defines my exact ground state energy. This is all he said. And interestingly, there's a lot of slip between the cup and the tea. You may think, but this is the beginning of formal DFT. So many have jumped the gun. Have they jumped the gun? I don't know. They may not have jumped the gun. They are probably right. But then many said, yes, energy is unique function of density. Which means I should be able to write energy in terms of density. Did Werner and Kohn say that? No. He never said that actually. So that is the reason it's very important for students to understand the proof. Because proof is all that he did. So there are jealous people who suddenly say, no, now energy can be done as a function of density. He never said what is the function. He only said there is an existence. So we can go back to the proof tomorrow when I start again. Formally, please think over it. The proof is of course very simple. That I again repeat, the two different external potentials, which are let's say one body potentials. So two different potentials should have two different densities. That is the existence. So that is the first part of the proof. So let's assume the contrary. That is, if I have V and V prime, two different external potentials, they still belong to the same density. Let's assume the contrary. Two different external potentials define two different Hamiltonians, but everything else is same except that's a very important thing, except with potential. Everything else is same. So when I'm going to do H minus H prime, remember my H minus H prime is nothing but V minus V prime. For a given an electron problem, of course. Nothing else is different. So then it applies variation method. So for H, I have a psi. For H prime, I have a psi prime. But the densities are same. That is what I assumed, and I will show that is not possible. So then it says that if I calculate psi H prime psi, it is greater than E naught prime. If I calculate psi prime H psi prime, it is greater than E naught. By variation method, because I have taken a wrong function. So I have taken a wrong function for H prime. Actual function is psi prime. I have taken psi, which is the function for H. It must be greater than E naught, and vice versa. Then you expand these two. You can easily see that if I expand this, I will get for this rho of r